ideas that we had in this chapter had to do with functions. All right? And before we actually started to look at a function, we looked at that idea which we call a relation. And let me write down an ordered pair such as 1, 2, 2, 3, 3, 4, and then I'll indicate that we have an infinite set here. And we have here a set of ordered pairs, and in fact, what then do we call a relation? But Sally says
any set of ordered pairs.
Just that. It is a set of ordered pairs, all right? A set of ordered pairs. And we weren't particularly interested in a relation as much as we were in that idea of a function. And what then did we say that a function was? And Mary Lou?
A relation with different first components.
All right. A function is a relation such that, I think these were some of the words that we used, such that for different components, what is our conclusion? There are what? For two different elements in the set, what then can we say about those, about the elements? All right, Ron?
There is exactly one.
All right, there is exactly one first component, is that right? Such that for different components, let's indicate it the way in which we looked at it initially. For different elements in the set, there are what? There are different what? First, let's indicate this by underlining the word first, elements. Is that right? Perhaps I should have interchanged the word components. We're using the word components and elements interchangeably here. Well, I think perhaps we had better look at a few examples just to make sure that we understand what we mean by this definition of a function. All right? In which we have different first elements. Now, there was one way in which we described a function, in which if you remember, if we make a diagram such as this, let me take 1 is mapped into the element 2, and let's say 2 is mapped into the element 3, 3 is mapped into the element 4, and x is mapped into, and what then, Todd?
X plus 1.
X plus 1. And what did we call this mapping, Brenda?
We call it a mapping diagram.
A mapping diagram. All right, very good. A mapping diagram. And then we gave this first set here a name, and Sally says
We call it the domain.
this is called the domain of our function, and then also we call the second element, Chuck, the range of our function. All right. Now there were some other words that we used to describe this, in which if we call this element in our range the image element, there was a name that we gave the element in the domain, Bob. The pre-image element. All right. And then there were some other words that we used. If we call this element the argument of the function, we also gave a name to the second element, Chip,
Which is the value.
called the value of the function. All right. These are all words that we used to describe a function and to talk about a function. All right, and then let's see now, there's another way in which we can talk about a function, and that is by means of a table. And if you remember, if I were to, let's take the same example, put down 1 and 2 in this fashion, 2 and 3, 3 and 4, and then some dots here, x, and then what element am I going to write in here? Let's indicate this bar by x plus 1. And if I were to use the variables x and y in this fashion, is that right? We have here a table which will describe a function, okay? And then in fact, if we also may think of a function in terms of what we may call a rule or a formula for the function, all right? In which we learn that we may use our set notation, in which we may write the set of all x comma y such that, and if I use the same example, what would the formula be for this example here, Todd?
Y equals x plus 1.
Here we have y is equal to x plus 1. By the way, if we were to look at an example such as this, we made another agreement about the domain, and remember we decided to take what? The domain to be that set, Brenda?
Of all real numbers.
The set of all real numbers for which the function is well defined. Is that right? Occasionally we have to exclude the number 0 or a number in the denominator which will make the value of the function undefined. Very good. Well, let's see now. There were perhaps 1 or 2 other ways in which we looked at a function, and there was one way, if you remember, in which we talked about this function machine. And let's look at that again. Remember we made this little box in which, let's electrify this box by putting a button on it. And if we had an element, so let's use the same example, 1, which we put into the machine, and we push the button, out pops some number. In this case, let me take the same example of 2. And if I put in the element 2 here, out will pop the element 3. And of course, if I, let's then indicate this by some element x. I push the button, and what element then are we going to have come out of this box, Steve? In which we'll have x plus 1. And then if we had put a label on this box to indicate what it does, Sally says
Y equals X
a
plus Y.
formula would be y is equal to x plus 1. Okay? Here's another way in which we can describe the function. And remember, this was a neat way in which we can talk about a function that is a relation which was not a function, because if we put in a number and push the button, and if the machine had to make a choice, remember it jammed. And that tells us that it's looking for one element in the range, and in fact there are going to be 2 elements, and that then is not a function. All right? There was another way in which we described a function, and that was by means of a graph. And for example, in the case that we have here, if I make a little coordinate axes here, x and y, in which looking at the same example of y is equal to x plus 1, we know that if it has a y-intercept of 1 and a slope number of what? Of 1 also. Well, let me decide to run 2 and rise 2. Let me pick out an arbitrary unit of measure in this fashion. And through these 2 points then we have a line in which this is the graph of the function. Is that right? What then was the formula for this function that we're talking about, Sally?
Y equals X plus Y.
Again, y is equal to x plus 1. And remember the graph test that we may give a function. If we look at the graph and we want to decide whether or not we have a function, remember how we thought about that as a line parallel to the y-axis, right? And wherever it intersects the curve or the graph, does it intersect it at exactly 1 point? And what's your conclusion about this function here, this straight line that we have here? I think you'll all agree that it is a function. Is that right? And then I think there are 1 or 2 other things that we considered. One of them had to do with notational devices, means by which we talked about functions. We use the letter f such that, and in fact the case that we have here, y is equal to x plus 1, we have already been using. There's another notational device using that f of x notation. And how then may we write that in the example that we have here? Todd? F
X in parentheses.
of x, all right, that's how we say that. F of x
Equals.
is
X
equal
plus
to x plus 1, all right? And then in fact there was this third way in which we thought of it in terms of this mapping, this dynamic idea of x being mapped into another number. Chuck says
You have x, it's mapped into like a narrow sign.
x is mapped into
X plus 1.
x plus 1 is another way in which we talked about a function. Okay? Very good. Now, after we went through some of these ideas of a function, we then looked at a number of special cases, and let's indicate that right here, in which we had some special functions. All right, some special functions. And one of the first functions that we considered was that of a linear function. And in fact, we have been looking at a linear function for a long time now. What was the formula, the general formula for this linear case, Steve?
Y equals mx plus b.
Y is equal to mx plus b, all right? And if we were to make a graph of it, in fact, we have already made the graph of one of these. Well, let me indicate any line in this fashion in which, why do we call this a linear function, by the way? Why is this given the name linear function, Brenda?
Because its graph is one straight line.
Because its graph is a straight line, and I think from what we have here, you'll agree that we do have a function. All right, then there was another example of a linear function that we considered, and that was what we called a constant function. All right? And does anybody remember the formula for the constant function? And Bob?
Y equals b.
Y is equal to b, in which the slope number is 0. If you were to make a graph of this, what then would that graph look like? And Brenda?
A horizontal line parallel to the x-axis.
All right, a horizontal line passing through some number. Let's decide to call this number right here what? This number here is b, is that right? And this then is the graph of the function y is equal to b, which is a constant function. All right? There was another special case that we call the identity function. And does anybody remember the formula for the identity, Todd?
Y equals X.
Y is equal to x, okay? And if I were to make the graph of the identity function, y is equal to x, what does that graph look like? And does anyone remember what that graph is like? Chuck?
It's a line passing through 0
Passing through 0, passing through the origin
with a slope of 1.
with a slope number of 1, okay? And the line is going to look like this, in which its equation is y is equal to 1, and y is equal to x, all right? And then let's see now, there were some other examples that we consider. By the way, all three of these are certainly a constant function, and the identity function is an example of what? These are certainly linear functions, is that right? And then we looked at another situation, another type of function, which was not linear, which we call the absolute value function. And what was the formula for the absolute value function, Sally?
Y equals the absolute value of
All right, in which we use these two parallel bars to indicate the absolute value function. And does anyone remember what its graph looks like, in which we have, Barb?
It's a line that goes to the origin with a slope of 1.
Through the origin with a slope of 1, all right? We may think of that as a half line, so to speak, all right?
And a half line with a slope of 1 on its side.
A slope of, not of 1, of negative 1 in this direction, is that right? In which we have there y is equal to the absolute value of x, which is, this is the graph of that function. Is that right? Okay. Now remember, we define the absolute value of x as a non-negative number, and think of your graph, your ordinate value, which is certainly non-negative. Is that right? And there is its graph. There was another special function that we looked at that was given a special name called the greatest integer function. And the notation that we used, if you remember, was this heavy bracket symbol. And remember, the greatest integer function was that integer, and the greatest integer, which is less than or equal to this number x. Is that right? And if you remember what the graph looked like, it was a, well, let me just indicate it, through the origin, and then a heavy line, and then at 1, it had a hole, and then it jumped. And then it had a hole, and it jumped with a hole, okay? And so on in that direction. At negative 1, it was down at negative 1, in which this point was on the graph and a hole. Is that right? This point's on the graph and a hole. This point's on the graph and a hole. And there was another name that we gave this function, and you remember what the popular name for it was, Ron?
Step.
A step function, because indeed it looks like a set of steps, okay? And we looked at this example as another example of a function. By the way, what is the domain? What domain could you take here for your values of x? What numbers could we select for our domain in this function? Can we have, Brenda?
all real numbers.
All real numbers would be its domain. What can you say about the range of this function? What values do we have for the range? Notice here is like -3, -2, -1, 0, 1, 2, and so on. What do you think the range might be, Steve?
All real numbers.
All the real numbers? Well, what do you think about that, David?
All the non-positive,
Non-
all the negative real numbers.
Negative real numbers. Chuck, what do you
All the
think?
natural.
All the natural numbers. Well, Chip,
All the integers.
all of the integers. I think, in fact, we have here the set of integers as its range, all right? All right, every number then from the domain is going to be mapped into an integer. Okay. Well, let's see now. We then went on and looked at some other functions, other examples of functions. There was a type of function that we call a polynomial function of degree 2, and we gave that a special name. And what was the name of that function, a polynomial, Jane?
Quadratic.
A quadratic function, all right? In fact, a linear function would be considered what? This example of a linear function, coming back here, is what? A polynomial of, Ron?
Degree 1.
Of degree 1. And in fact, I think we also gave a name to a constant function. Y is equal to b is a polynomial function of degree 0, except when the constant itself is 0. And if you remember, that function we did not give a degree number to. Okay? So what then was the general formula for a quadratic function? Sally?
Ax squared.
All right, let's think of it in terms of a function of notation of y is equal to
Ax squared plus bx.
ax squared plus bx plus c. And in fact, there is some restriction that we must put, David.
And A is not equal to 0.
The restriction on a that it cannot be equal to 0, because if it were equal to 0, you're right back to the case of a linear function. Is that right? Okay. And then we did a little bit of work with the graph of this type of function. In fact, in Chapter 11, we're going to do a lot more. And let me just make a graph which might look like this. in which here's our x and our y-axes. And right here at this point, through this point, we have a vertical line. And that line we gave a special name. Todd says
Axis of
this was called our axis of symmetry. All right, our axis of symmetry. And this point right here was given a special name. And Bob?
minimum point.
In this case, it's a minimum point because our graph opens upward. Is that right? And in fact, if our graph opens upward, we had another name for this, by the way, Sally.
Vertex.
The vertex point. And because the graph opens upward, in fact, Bob says that it is a minimum. All right? And we also gave these points a special name where the graph crosses the x-axis. Ron?
Zeros.
The zeros of the function, okay? The zeros of the function. By the way, what kind of a graph do we have here? We gave a name to this graph. David?
Parabola.
This is called a parabola. P-A-R-A-B-O-L-A, all right? And there was one characteristic from our equation here, from our formula, that told us that its graph is going to open upward. And in the case that we have here, what then decides that, Brenda?
A is greater than
That the number a here in our formula is greater than 0, okay? And then if we were to consider another case in which, oh, suppose, for example, our graph looked like this, all right, in which here is our axis of symmetry, and there is some point, what then is your conclusion about the number a if this is its graph? What do you know about a, Sally?
A is less than
That in this case, a must be less than 0. The graph is going to open downward. Here we still have these as our zeros. This is still our axis of symmetry. And in fact, because it does open downward, what then is that vertex point going to be? David?
Maximum.
It's going to be a maximum, okay? This was the quadratic function, and as I said in chapter 11, we're going to study this function in much more detail. Then there was another function that we considered, and that was a polynomial function of degree 3, which we gave another name. Chuck?
Cubic.
That was called a cubic function. And in fact, the book didn't do too much with a cubic function, but there was a formula, a general case of this cubic that we looked at. Todd?
Ax cubed.
All right, let's talk again in terms of y is equal to,
Ax cubed
here we have ax cubed
plus bx squared
plus bx squared
plus cx
plus cx
plus d.
plus d, where
Equals 0.
again we have the restriction that a cannot be equal to 0, because if a were 0, you're back to the quadratic case, okay? And we didn't take very many cases of this cubic function. In fact, we took just one or two very special cases, but I was more interested in a general pattern that emerged from this cubic function. And if you remember, a cubic function is one which might have this shape, in which the function, the graph, might look something like this if we were to consider the graph. Notice, by the way, in this example, how many zeros do we have? And David says
3.
we have a total, it looks like we have 1, 2, 3 zeros. And because I drew the graph in this shape here, what is your conclusion about the number a? What do you know about a, Todd?
A is greater than 0.
In this case, a is greater than 0, because if a, in the case that we have here, when a is greater than 0, a number, when multiplied by itself 3 times, a positive number is certainly going to be positive, and a negative number times itself 3 times is going to be negative. Is that right? When a is positive. So indeed, our graph is going to increase from left to right. As x moves across the graph from left to right, the value of the function increases. Okay? And then, in fact, there was the other case that we considered, in which, oh, let me just take a graph that looks something like this, in which here's our x and our y-axes. And what's your conclusion about the number a in this case, Todd?
A is less
And here we have the case in which a is less than 0, because a negative number times a negative number cubed is going to give us what? A number which is, a negative number cubed is what?
negative.
Negative times another negative number is going to give us a number which is positive. So in fact, the graph has to decrease from left to right. Is that right? Okay. By the way, let's look at one or two other examples of odd degreed functions. Suppose we had x to the 7th power. All right, x to the 7th power in which the number a, say, is negative. Is the graph going to look like, say, the one here on the left, or on the right rather, which is going to decrease, or is it going to look like the one here on the left? Chip?
It's going to look like the one on the right.
The one on the right. In other words, it's going to be a decreasing function. Is that right? How many times will that graph cross the x-axis? What do you know about it? How many zeros must it have? What do you know about the zeros of that function, Sally?
At least one.
There has to be at least one, is that right? If then indeed the degree here of our function is an odd number, at least one, because it's going to have to either be an increasing function from left to right or a decreasing function in which it's got to cross the x-axis at least once. Okay? Well, let's see now. After we worked with some of these special functions, another big idea that we considered had to do with variation, all right? And one of the first types of variation that we considered was called direct variation. And what was the formula for direct variation, Chuck?
Y was ever.
Y is equal to m times x. And we had a restriction on the number m, which again says what? That m cannot be, Todd?
0.
M cannot be equal to 0. Let me include that right in here, in which, in every case, I think we have to exclude 0 as a value for m. By the way, what number did we call m? What was the name that we gave that, David?
A variable.
It's well, not Ron. That was the constant of variation. What is the variable in this formula? Is on the right-hand side, what then is the variable that we have here, Steve?
X.
X is certainly going to be the variable, all right? Now, let me, if I were to take a particular value of x, that would give us a particular value of y, in which we use the notation y sub 1 is equal to m times x sub 1. If I have another particular value of x, which we'll call x sub 2, that will give us a special value for y sub 2. Is that right? Now, if I were to divide both sides through here by x sub 1 and both sides through here by x sub 2, then lo and behold, they're both equal to m. Therefore, what is your conclusion about these two sentences? And what can you say there? Chip?
Y sub 1
Y sub 1
over x sub 1
over x sub 1
is equal to y sub 2 over x sub 1.
y sub 2 over x sub 2, okay? And in fact, we call this a proportion. Let me come up here and write this proportion. Let me rewrite it. Y sub 1 is to x sub 1 as y sub 2 is to x sub 2. And there was another way in which we learned how to write that. Y sub 1 is to x sub 1 as y sub 2 is to x sub 2 using this colon notation. And when it's written in this pattern, it's quite obvious by looking at these two numbers in the middle here, and we gave those two numbers a special name, Steve.
The means.
These are called the means. And then the two numbers on the ends here were given a special name, and we refer to those, Sally, as the extremes, okay? And now coming back and looking, well, let's look at this statement first. There was a pattern, a rule that we learned, which, a verbal statement which we can make about the means and the extremes. And what was that, Todd?
Product of the means equals the product
All right, the product of the means is equal to the product of the extremes. And if you were to look here at this pattern, right, here we have which two are these right here? X sub 1 and y sub 2 are called what? Those are the means. The product of the means is equal to the product of the extremes. Okay? Well, let's see now. There was another type of variation that we considered, and that had to do with inverse variation. And if I said y varies inversely as x, what then may we write, Chuck?
Y was m over.
Y is equal to m over x. Again here, m cannot be 0, and also what other number cannot be 0? And what else can we say? X cannot be equal to 0. Is that right? Okay. And let's look at the graphs of these functions, of this particular type of an inverse variation function. And if you remember, one of the graphs that we made was such that it looked like this, in which here is our x-axis and our y-axis. And what name did we give this function, Chip?
A hyperbola.
And hyperbola, H-Y-P-E-R-B-O-L-A. And in the case that we have here, what can we say about the number m? And what can we say here, Brenda?
M is greater than 0.
In this case, we have m is greater than 0. And in fact, if I were to make another picture over here, in which the graph ended up in the second and the fourth quadrant, such as I have here, what then can we say about the number m in this case, Sally?
M is less than 0.
In this case, we have m is less than 0. Okay? Well, let's see now. By the way, not only can we have as an inverse function y is equal to m over x, but we might have, say, something like y varies inversely as the square of x would be another example of an inverse variation function. We're not going to consider the graph of something like that, but in fact we may use one in our examples. There was another type of variation that we looked at, and it was called a joint variation. If I said that y varies, or say z varies jointly as x and y, Todd?
Z equals mxy.
Z is equal to m times x times y would be an example of a joint variation. Or how about a varies directly as the square of b and the cube of c would be considered a joint variation, all right? And then, in fact, there was another type of variation that we had, and we call that a what? A combined variation, in which, an example might be z varies directly as x and inversely as y. And Sally?
Z equals mx over y.
Z is equal to m times x over y, or a varies directly as the square of b and inversely as the cube of c, for example, would be an example of a combined variation. Okay? In fact, let's look at one or two examples of variation. Here we have a problem in which we have the gravitational force of attraction F between two objects varies directly as the product m of their masses and inversely as the square of the distance d between them. If two objects 3 meters apart, whose product of their masses is 12 kilograms squared, have a gravitational force of attraction of 0.002 dynes, what is the gravitational force of attraction when they are 2 meters apart? Wow, you read all of that and you say, oh my heavens, I have no idea what they're talking about. I don't know anything about dynes, I don't know anything about kilograms squared, and in fact, you don't really need to know too much about that. The emphasis here is on the idea of a proportion and of one of our variations. So what type of variation do you think we are dealing with here, looking at this first sentence? What then does it say? The gravitational force of attraction F between two objects varies directly as the product m and inversely as the square of the distance. Chip?
Combined.
It's a combined variation. So let's then take our variables here, and who would like to come up with a formula for this? Ron?
F is equal to
F is equal to
small m
m
times capital
times capital M. Perhaps that was a bad choice, but that's what most people take for mass in terms of the letter M. All right?
over d squared.
All over d squared. Okay? Now, again, for a particular value of the product of the masses and a distance, all right, we have then a particular value of f sub 1, and also for a particular value of masses, m sub 2, and a particular value of distance, we have a particular value of f sub 2, okay? And let's now try to get this in terms of m. So who would like to get this left-hand statement in terms of m? Kirby. What do you think? All right, we're looking for m is equal to something, or something is equal to m. Can you come up with any formula there? Todd?
F
F sub 1 here
F sub 1 times D
times
D squared sub
d sub 1 squared, okay,
over M.
over, in this case, m sub 1 is equal to m. And in fact, on the right-hand side, what can we say there, Kirby?
F sub 2
F sub 2
times d sub 2 squared
times d sub 2 squared
over m sub 2
over m sub 2 is equal to
m.
m, okay? And now, who would like to, what is your conclusion about these two? David?
They're both equal.
They're equal, okay? So therefore, we can set them equal. F sub 1 times d sub 1 squared over m sub 1 is equal to what? F sub 2 times d sub 2 squared over m sub 2, all right? Now, let's look at this sentence that we have here, in which we have 1, 2, 3, 4, 5, 6 numbers, of which we must know how many. In this case, we have, Barbie says, we must know 5 of them, and in fact, we then can find the 6th. So let's now come back to our data and see if we can't replace these variables with some numbers. If two objects 3 meters apart, so this would be in terms of what number that we're looking for in our sentence, in our equation, distance d, and that would be d sub 1, so let's call that number what? D sub 1 squared is what number?
9.
3 squared is 9, okay? Whose product of their masses is 12 kilograms squared. So that would be what number? This, in this case, would be what? 12 is a name for what? The product of their masses is what variable that we have here for the masses? The product of the masses, m sub 1, is in this case what number? Well, that's simply the number 12, is that right? It gives us a force of attraction. That's our F sub 1 of what? How many dynes? Of what? 0.002. Is that right? Okay. All right, is equal to, and now what then is the question? What is the gravitational force of attraction when they are 2 meters apart? So what then is our distance squared? That's a number 4. And what is the gravitational force of attraction? Is the number F sub 2 that we're looking for. And the product of their masses is still what? 12 kilograms squared. All right, now we're interested in solving this little sentence for F sub 2. And let's just multiply both sides by 12. Okay, and then we'll have what? 0.002 times 9 divided by what? By 4, all right? And now let's see, now 4 into 0.002 is what? 0.05 times 9. And what then is this equal to? It's what? 0.0045, all right? And so our conclusion is, the question asks, what is the gravitational force of attraction when they are 2 meters apart? And our answer is, what, 0.0045, and what is our unit that we are dealing with? Here, that many dynes. Okay? Well, let's look at a last example, and I think that's all that we need to do for today. If a varies directly as the square root of b, and inversely as c squared, and if b is multiplied by 4 and c is divided by 2, by what factor is a changed? Okay? Well, who would like to write a sentence which will pull all this together? Anyone? Sally?
A times
All right.
square.
If a varies directly as the square root of b, so let's take it one step at a time. A equals?
Square root of b.
All right, well, we need that constant of proportionality in there, Todd.
A equals
M
times the square root of b
times the square root of b
over c squared.
over c squared. Is that right? Okay. Now, let's call this a particular value of a, which I'll call a sub 1, and then we're going to do something to b and to c. All right, and if b is multiplied by 4, so who then would like to write a sentence which is going to take care of this? So let's call it a sub 2 is equal to something in which this original b is now going to be what? 4b. So there's m times the square root of what? 4b divided by, and c is divided by 2.
C over
And that's what? That's c over 2, all what? Squared. Okay, now let's work with that. Now here we have the square root of 4b is another name for what? What's the square root of 4 is 2. And there's 2m times the square root of b that we still have there. And another name for c over 2 squared is what? C, what? C squared over 4, okay, is equal to, and now let's just look at this and pull another name for the number 1 out of our hat, which is what number? 4 over 4, is that right? Because 4 times c squared over 4 is a name for what? C squared, and 4 times 2 is 8, and we have 8m times the square root of b. In fact, I may even write that 8 out front and have left m times the square root of b all over c squared. Now, there's a name for a sub 2, which is 8 times m times the square root of b all over c squared. And here's a name for a sub 1. So the question asked, by what factor is a changed? So what's your conclusion, Brenda?
It's multiplied by
All right, a is multiplied by the factor 8. Okay? Well, I think that's all that we need to do for today in this review. I hope this gave you an opportunity to see all of these ideas put together in one lesson. And let me give you your assignment for